Good evening, everyone, and welcome to this talk with Dr. Adam Durant. My name is Anne Cernek, and I joined Claire in February as a Senior Development Officer. I'm really pleased to be here tonight to have the opportunity to meet many of you in person soon. Our session this evening is being recorded, and the link to the recording will be made available tomorrow on our week website. So please do feel free to share that with anyone you think might be interested in hearing the talk. We will have lots of time for questions, so do write your questions into the chat function on Zoom, and I will ask them to Adam after this talk. You're more than welcome to post them before he finishes speaking. I'm delighted to introduce Dr. Adam Durant, who is a former college research associate of Claire and the CEO of SATAVIA, which he founded in 2013. SATAVIA is leading the way to enable aviation to reduce its climate impact. Adam previously worked with the Norwegian Institute for Air Research, where he joined a spin-out working on volcanic ash detection with Airbus and EasyJet. Adam, thank you so much for being here with us tonight. Over to you.
Thank you very much, Anne. It's great to be here. And thanks everyone for joining. So I'm just going to share my screen. Okay. So yeah, I founded SATAVIA with the purpose of making aviation smarter and greener. So today I'm going to talk about, first of all, a little bit about my journey, how I ended up starting SATAVIA, and then I'm going to talk about one of the big issues that we're trying to help solve, which is aviation's climate impact. So hopefully you can see a slide that shows me here. So yeah, I've come from science. So my background actually originally is a geologist. So I got my first degree from Bristol, but then I moved to Michigan Tech. And it's there that I started working with atmospheric scientists and doing some fundamental research on cloud microphysics. Following that, so I actually also specialized in volcanic ash clouds and looking at how water in volcanic ash clouds causes the ash to fall out of the atmosphere faster. And then I founded SATAVIA a bit later on, really to apply a lot of the knowledge that I gathered through doing a series of postdocs, which took me to places like University of Cambridge, Bristol again, and the Norwegian Institute for Air Research. So it was really this eruption back in 2010 that started my journey into entrepreneurship. So this is the Eyjafjallajökull eruption in southern Iceland. So it was a fairly small eruption in the grand scheme of things, but it contained a lot of fine ash because the volcano erupted through a glacier. And that caused widespread flight cancellations throughout Europe. So you may remember being stuck somewhere. An awful lot of people were trying to get back and it took them several weeks. But this is because volcanic ash causes a hazard to aviation, and the cloud got taken over the UK by a weather front, and it kind of then sat over Europe for about 5 days and caused lots of flight cancellations. So my first foray into entrepreneurship was working with a spin out of the Norwegian Institute for Air Research. So we were basically taking technology that was developed for satellite remote sensing of volcanic ash clouds. So looking down at the Earth's surface from space to identify water clouds versus silicate rich clouds. And what we did was we basically placed similar infrared technology on the wing of this aircraft, and we're flight testing it in various places like Etna, Stromboli here, and later flying out over to Morocco. But this, you can see here, this is the canister, contains a couple of thermo-infrared imaging cameras at different wavelengths. And so what we did there was we were taking simultaneous images at different wavelengths and looking at the difference, and using a technique called the split window technique, you can actually then discriminate between water clouds and ash clouds. The idea being we could take this technology to market and enable commercial pilots to be able to spot volcanic clouds ahead of the aircraft. I'm just sharing a video actually of us flying over Etna volcano here. So you'll see that's the pilot there. He's taking pictures. We're in a very small microlight aircraft, and that's the plume coming out of Etna. Sadly, we didn't get much volcanic ash when we were out there, but you can see beautiful plumes of sulfur dioxide and other nasty things coming out of the volcano. And we were able to do all kinds of flying in this small aircraft that you wouldn't normally do. You can see the pilot there is having a bit of trouble with the noxious gases coming out of the volcano. But anyway, so this was the kind of experience that really led me to set up SATAVIA, and then we moved. We were working closely with Airbus and EasyJet at the time. This is the A340 testbed aircraft that we then went on to do a series of tests out of Toulouse. So I learned an awful lot about the industry doing this work, and it really formed the foundation for me then going off and setting up SATAVIA on my own. That's the inside of the aircraft. You can see it's packed full of instrumentation for flight test. So yes, set up SATAVIA in 2013. We started off very small. We've now grown to over 20 people, and I guess one of the most great moments of recent times was actually getting featured in New Scientist because of our work on contrails. So we're based in Cambridge, UK. We've got offices up in Castle Park, and we're a fairly dynamic team. So we combine people with backgrounds in data science and AI, data and software engineering, aerospace engineering, and atmosphere and climate science. So all of that is encapsulated in the software that we build. And we're also quite focused on generating fundamental scientific research at the same time. So here's some of the key science team. So we've got Dr. Greg Thompson. Actually, I'm dialing in today from Colorado. I'm actually with Greg today before flying back to the UK. But Greg's got nearly 30 years worth of experience doing weather modeling, specifically looking at how icing impacts on aircraft and affects the safety of aircraft flight operations. But we're using a model called the WRF model, and he's actually an author of that in terms of the cloud microphysics that's in the weather forecast model. So that's used by organizations around the world daily to do weather forecasting. So we've taken a lot of Greg's knowledge and past experience and put it into the technology that we're building. Dr. Daniel Bannister, he's our Chief Scientific Officer. He comes from the British Antarctic Survey. Ritik Bhattacharya is a recent addition to the team. He's a very strong atmospheric scientist and worked at places like Caltech. And more recently, Professor Rod Jones, who is Vice President of Queen's and also holds a position at University of Cambridge Chemistry Department. Well, I actually used to work for Rod, but he's recently joined as an advisor, and he brings a vast wealth of knowledge on atmospheric chemistry and cloud physics to what we're doing. So some of the customers that we actually have today are shown here. It's mainly the aircraft engine OEMs, and also you've got the airframe OEMs like Airbus. We've done a lot of fundamental product development. So we're building new stuff. We've had a lot of support from the European Space Agency and the Aerospace Technology Institute. We've forged partnerships with the likes of Microsoft and AWS. So we've built our technology in the commercial cloud that enables us to scale up the compute and the storage quickly and efficiently. And more recently, you'll see on the right-hand side there, some of the supporters. So there's one of those is listed as Aviation X Lab. So this is a Dubai-based incubator. We've just finished a 12-week program with them, and it's got the support of organizations including Emirates Airline, Airbus, Thales, GE, and Collins. So some of the biggest names in aerospace. It's an innovation initiative, and we were one of 2 companies selected to go and work with them in Dubai. So I'm actually on my way back from Dubai. It's just taking a little bit longer than usual to get back to the UK because I've stopped off in the US. But some of our achievements this year, so we got recognized as one of the UK's fastest scaling companies by Silicon Valley comes to the UK. We were in the top 50 EU companies last year. And we also just got shortlisted for the COGEX Climate Innovation Award. So we're really proud of some of the achievements that we're making. And of course, we've also been picked up by some of these quite well-known media outlets. So on to the subject of the talk. So it's really about the climate impact of aviation. And the key message here is that carbon is not the only thing we should be thinking about. So there's a lot of discussion of carbon emissions from aviation. It's quite clear when you burn tons of kerosene on every flight, it generates an awful lot of carbon dioxide. But it turns out that most of the climate impact is actually coming from the clouds that the aircraft make. So these are called contrails, short for condensation trails. And I'm going to explain a little bit more about what's going on in those clouds, but essentially they are clouds of water, usually formed from water in the emissions. So when you burn kerosene, you not only produce carbon dioxide, you also release water. And when you fly through the atmosphere, in certain conditions, you can create these contrail clouds. So why are they a problem? Well, first of all, in 2019, there were nearly 100,000 flights per day around the world. So there's always an aircraft flying somewhere, and most likely there's always an aircraft making these clouds somewhere. And you can see on this satellite image on the right side there that there's lots of streaks over the Gulf region. So those are aircraft contrails, and sometimes they can sit there for many hours. Sometimes they can even go on to grow and create complete layers of cloud. So the problem is, I'm going to explain this a little bit more, that they create, on average across all flights, a surface warming effect. So this is due to the small ice particles in those clouds, and those ice particles interact with heat that's coming from the Earth's surface. If the cloud wasn't there, the heat would go to space, but the cloud absorbs some of that heat and radiates it back downwards to the surface. It also interacts with sunlight, but on average across all flights, it's a warming effect. So for industry, it's not really an issue to them at the moment because there's no regulation that says they need to do anything about this issue at all. However, it's been known for quite some decades that contrails actually do have an impact on climate. There's been a bit of uncertainty in the science up until recently about how they affect the overall forcing from aviation, but it's pretty much coming to agreement now scientifically that they're an issue and they cause surface warming, and that is driving regulation. So regulation is coming, and hopefully the industry takes some proactive on this before they're actually required to. So today, airlines are required, if they fly in European airspace, they're required to report their carbon emissions under a scheme called CORSIA. So this is the European scheme that tracks how much carbon emissions aviation produces from flights in and out of Europe. EASA, which is the European Aviation Safety Authority, just put a paper out this year which lays the framework for actually bringing in regulation that focuses on the non-CO2 effect. So that's not only the clouds that the aircraft make, but there's also other gases like NOx and small particles, soot particles, which have an impact on the overall forcing. So they're going to have to do something about it soon. So the regulation is coming. And not only is the regulation coming, but airlines now are very focused on their green credentials, and they are investing in what's called carbon offsetting. So they put money into projects that counter the carbon emissions. So quite often you'll hear airlines talking about planting trees. There's a real question around whether that is the right approach, but they can pay to offset some of their carbon, and somebody somewhere else grows some trees to offset that carbon. So there's actually a trial taking place today in Europe. So this is an organization called Eurocontrol. So Eurocontrol is an air traffic management organization. They are concerned with tracking aircraft flight movements and ensuring the safety of those flights. So they're also working with a German organization called DLR. So DLR is an aerospace research organization, and they're currently doing the first trial where they're radioing the pilots via air traffic control to change flight levels. So by changing flight level, you can actually prevent some of the contrail formation. I'll explain this all in a little bit. So bottom line is there is some action being taken, the regulation is coming, and the industry will have to take this issue seriously in the near future. So here's an image of an aircraft flying above another aircraft, and it's making this rather beautiful contrail cloud. You'll note that the cloud is coming off the wings in this case. So this is really interesting because contrail clouds can actually form due to the turbulence of the aircraft passing through the atmosphere. So it all comes down to how wet the atmosphere is in the first place, whether or not it's saturated. So saturated air is full of water and it's ready to make clouds. So sometimes the motion of the aircraft through the saturated atmosphere can cause the clouds to form. The rainbow colors here are actually caused by small ice crystals diffracting sunlight. So you get a rainbow effect as you look through the cloud, and it's due to the shape of the crystals. Now this is a movie of, it's a Dreamliner aircraft, so that's a Boeing 787, one of the most modern aircraft around, and it's flying below another aircraft. And you can note some really interesting features here. So you have these two big rolling clouds coming off the wingtips. Those are called vortexes. So this is where the air is passing over the wings and then forming a spiral. And then you can start seeing cloudy air coming out of the engine. So that's the water coming out of the engine. So you've got the effect of the rolling wave vortices plus the water being emitted by the engine. So that creates this geometric cloud here. You can see sort of cylindrical 2 cylinders, and that's the first point of nucleation of those ice crystals that are in that cloud. The reason they're ice is because aircraft cruise at altitudes where the temperatures may be -50 or -60. And when it's that cold, the water that's present in the atmosphere forming clouds is always in an ice form. And so here you can see an image which shows busy airspace on a contrail forming day. And it's a day in which the contrails will sit around for many hours. So they're called persistent contrails. And you can also see a spreading of them. So that initial event where you have the aircraft going through seeds the cloud. And then because the atmosphere was already ready to make clouds, but hadn't quite made them, they are there, the ice crystals are then nucleated. Once they're nucleated, if the atmosphere is wet enough, those clouds can go on to grow and form these complete cloud layers that can span whole regions or even continents. So I'm just showing you now an image of some of the work I did as a graduate student at Michigan Tech. So did you know that water doesn't actually freeze at 0 degrees? You have to actually undercool the liquid water in order for it to change from liquid water to ice. So there's a latent heat of fusion that's required. That means you've got to put energy in before, or take energy out, sorry, before it will actually do that phase transformation to a more stable phase. So what we're going to see here is a cooling of a water drop with a volcanic ash particle in it. And that ash particle actually acts as a nucleus for the ice formation. It helps to form the ice phase at a warmer temperature. And when the ice actually forms, it releases heat. So that's the latent heat of fusion. You're going to see it on the measurement as the temperature has dropped. So it releases this pulse of heat, and then it is in the solid phase. Well, that was sort of some of the work that led to me getting involved in what we're doing here. But as you look at what's in clouds as you get colder, so this is a plot showing temperature on the x-axis. So it goes from 0 degrees and gets colder to the right. And as you go upwards, the atmosphere is actually getting wetter. So where it says 0 supersaturation, that's when you've got a relative humidity of 100%. It actually, in nature, you usually have to go maybe over 102, 103% before you actually get these cloud particles forming naturally. Sometimes they form on dust particles, but they can also form what's called homogeneously. And that's when you get the air cold enough, the water doesn't need anything to catalyze that anymore. And that usually happens at -40. So where aircraft are flying, actually, you don't need particles to catalyze that. But what this plot is showing here is, depending on the temperature and the supersaturation, the amount of water in the atmosphere, you get different shapes of ice crystals. And these are really small as well. So here's some images of natural ice crystals. These are probably only tens of microns in diameter. So you've got these needles on the left, you've got dendrites in the middle and plates on the right there. And so all of these are reflecting the temperature and the amount of water in the atmosphere, and also maybe the history. So the one on the bottom left there, you see, you've got this column in the middle, hexagonal column, and it's got some plates attached to the end. So that might indicate the central part formed at a high altitude. It's then started settling down into warmer parts of the atmosphere, and then it formed some plates on the end. So beautiful structures formed by nature. These structures actually interact with the heat coming from the surface of the Earth differently. So when we model this effect, we have to take that into account. Okay, so some fundamental research that came out recently looking at the global aviation climate impact budget. So this was work that came out of Manchester Metropolitan University, and they looked at 18 years worth of climate data. And they did some modeling, and they looked at all of human forcings on climate. So that's things like land use change, manufacturing cement, for example, all kinds of emissions from industry. And they also looked at aviation. And so they determined that aviation actually accounts for 3.5% of total human impact on climate. But 2/3 of that is coming from the clouds that the aircraft make, while only about 1/3 is coming from the carbon emissions. So in terms of the carbon budget, aviation accounts for about 2.9% of all carbon emissions. But if you take into account the indirect effects, the effects from the clouds, aviation accounts for 3.5%, and about 2 times as much of that forcing is coming from the clouds versus the carbon emissions. So here's a sort of a schematic of how this actually works. So we've had a look at now the nature of the ice crystals in the cloud. You also get some gases emitted. You can see on the bottom right there when you do combustion. So you've got the carbon dioxide, the nitrogen oxides, you get some carbon monoxide, sulfur species. Those form small aerosol particles. You get some soot as well. So it forms this cloud of gases and particles, and it sits there and it's interacting with the heat coming from the surface of the Earth, but also sometimes if it's sunny and it's daytime, then it will potentially reflect some of that sunlight back to space. So the overall forcing from those clouds is dependent upon the difference between the amount of sunlight coming in and being reflected versus the amount of heat that's coming up from the Earth's surface and being reflected back downwards. So they've looked at this, done the budget, and determined that, well, this is Aviation's climate impact now in terms of what's called carbon dioxide equivalent units. So we know how much carbon dioxide is emitted overall because we know how much kerosene was burned. It's a fairly simple conversion to go from mass of kerosene, you multiply by just over 3, and you get to mass of CO2 emitted. It's consistent, then the CO2 gets well mixed from the surface to space in the atmosphere, and then it directly interacts with sunlight coming in and warms up slightly. So we can model that well. It's well constrained from the amount of kerosene that's burnt, and we know that pretty well. However, there was a residual when they looked at this. And so most of that was attributed to the clouds that the aircraft make. When we do the radiative modeling, we can then look at what the forcing is at surface. So forcing is the effect of the clouds in this case on climate, and we do it in terms of watts per meter squared. So watts per meter squared is the amount of energy that those clouds actually direct back at the surface. And then we can do a final conversion into an equivalent amount of carbon dioxide that would do that forcing. So then we can compare contrails with carbon emissions. So these are the actual masses in terms of the carbon dioxide equivalent forcing from all of aviation. So it's nearly 3 billion tons of carbon dioxide equivalent, nearly 2 billion tons of carbon dioxide equivalent forcing per year from contrails across all flights. So those are very big numbers, but I think we can do something about the middle one, which is managing those contrails. So that leads us to the technology that we've developed. So we've built a software platform. I'm going to tell you about that in a second, but it enables us to do very high resolution weather forecasting. And you're seeing our products now on the screen there. So these red areas are airspace where we're very certain that if you fly an aircraft through it at a certain height, at a certain time, then you're going to form a contrail and it will sit there for long enough that it will have an effect on climate. So the solution is actually to adjust the height of the flight plans that airlines produce, or maybe even the routing So you can adjust X, Y, and Z to manage this problem. So all it points back to is smarter flight planning could take out up to 60% of aviation's climate impact, which is actually 2% of all human impact. So it's a simple data analytics solution that can solve a huge amount of climate change. Our technology is called 5DX, so it's a software platform. So we take data from satellites, we use high performance compute to run a numerical weather prediction model called WRF, and that enables us to create a digital twin of the Earth's atmosphere. Once we've done that, we can then run a model that predicts contrail formation. The idea being then we can integrate with the airline's IT systems and feed that information back into their flight planning software. So here's just a schematic showing the model. So we break the Earth's atmosphere down into 6 billion model cells. So that's 5 by 5 kilometers at the equator. We go up 60 levels to 60,000 feet. And at every single cell, we do 100 algorithmic computations. We get about 26 meteorological parameters coming out to do a 24-hour simulation of the Earth's atmosphere and weather at 30-second time steps. Means that we do about 1 quadrillion computations for every 24 hours that we simulate the Earth's atmosphere. So we did an experiment with, or demonstration with Microsoft in December of last year, where we actually scaled the high performance compute to all of their available resource for Western Europe. And we were able to simulate 2 months worth of European weather at really high resolutions, and get the results in about 5 to 6 hours. So that's really where the technology's got to. So back to the product. So this is a closer view now of a layer through our contrails prediction capability, if you like. So you see on the x-axis on the bottom there, we've got a 24-hour forecast, and on the y, we've got different levels. So we can actually, at every level, we can predict where we're going to form contrails. As you go lower or higher, it turns out you don't really make contrails. The atmosphere is too dry. It doesn't matter if you add extra water to it from the engines, it's still too dry. Aircraft today are designed, rather unfortunately, to cruise at their optimal cruise altitude, which is also in the best place for making contrails. So in the future, probably the OEMs will be looking at changing the design of the aircraft so they cruise lower or higher. But today, aircraft cruise in the sweet spot for making contrails. So that leads us to what we're trying to do with the airlines. So today, what we can do with them is exactly what you've just seen, smarter flight planning. We'll integrate that into flight planning software. And we're also trying to build a business model around this to generate any changes that they make to their flight plans into carbon offset credits. So I'll just talk through some of these. So airline flight planning, this actually starts a year before the flight takes place. So the first thing to do is to design the schedule. So this is basically a list of daily flights from city A to city B. And that is done according to predictions of what travelers are going to want in the following year. So COVID really has made a mess of a lot of airlines' schedules, and that's why we see a lot of aircraft sitting on the ground at the moment. When you get closer to the day of the flight, maybe 12 weeks, we can start assigning specific aircraft, or at least fleets of aircraft, to clusters of routes. And then 2 to 4 weeks down towards the flight, we get down to the individual aircraft and the crew that are going to fly the specific flight. So that's the sort of precursor to doing the flight planning. You get all your assets and your human resources in place. And then on the day, there's a process called flight planning. So this is primarily done to make sure that the aircraft flies the most efficient route. It has to take off at a set time and arrive at a set time. And it has to deal with weather en route, other traffic, hazards, and it may need to fly over certain points, waypoints, for safety reasons or for other reasons. And on the day, the rules for air traffic management may change. So in certain parts of the world, like Europe, it's very busy, and aircraft have to fly in very specific corridors and between narrow flight levels. So all that has to be taken into account, and that at the end of this process, a trajectory is planned. So it estimates the amount of fuel that's required, and it's turned into a flight plan that is given to a pilot. That flight plan is a list of waypoints and flight levels that the aircraft will then fly. And usually most of that is done under autopilot. Carbon offsets, you may have heard about these things. So the airlines, as I mentioned, are paying to offset their carbon emissions. A lot of them are talking about planting trees, but I think actually where we need to get to is putting these offsets back into renewable energy production. So creating projects that generate green energy, and that green energy ultimately in the future could be used to make green hydrogen, which could be used to make sustainable aviation fuel. So really we want to do a closed loop offsetting where initially the airlines are paying to help produce the sustainable fuel of the future. But the reason I mention this is we're trying to create what's called a project. So we're going through an organization that certifies methods, turns them into projects. That means if the airline takes some action, in this case, it's changing its flight plan, and we can prove that we've prevented some climate impact, and we can convert it into a carbon dioxide equivalent mass, then we can enable the airline to trade that on a voluntary emission trading scheme. They could either monetize it, or they could then put it to offset their carbon emissions. So that's really where we're trying to get to. That'll probably take us a couple of years. I'm just going to end by sort of updating you on an engagement that we just have completed. So this is the Aviation X Lab. It's a Dubai-based incubator. You'll see me third on the left there. Gentleman in the white is the Chief Operating Officer of Emirates Airline. So it's the biggest airline in the world, one of the biggest Middle Eastern airline. And they have created this innovation initiative to enable companies like ours to come and test ideas with an operational team. So in this case, we worked with flight planning and we did a series of dry run flight planning exercises where we actually generated viable flight plans that avoided contrails. So it's the first time anybody's done this with an airline using commercial flight planning software. So the way it worked was the day before we were actually going to change the flight plan, we did a long-term 36-hour forecast. The reason being, we then analysed their entire list of flights for the following day, and we chose a very small number of flights that would spend the longest time in contrail forming conditions. So it actually turns out we don't need to change every flight. It's actually probably less than 5% of all flights that actually generate contrail forcing that has an impact on climate that we should be concerned about. So in this case, we were doing 2 a day. We would predict which flight numbers would be most impacted the following day. And then on the day of the flight planning exercise, we'd request what's called the briefing pack. So these are a document that gives the flight plan, which is basically the track you can see there, and the flight levels to fly. So with a flight we first analyze all flights that we look at. So you can see in the bottom right there, a cross section, a slice through the output from our contrail prediction. And the black dotted line was the original vertical profile. So this is the height the aircraft flies at. You'll see as the flight goes on, the profile goes up. The aircraft's getting lighter. It can cruise at higher altitudes where the air is less dense and you get more efficiency. However, when you could fly through these regions forming contrails, the climate impact from those clouds is actually quite significant. So we developed an algorithm that actually found the most optimal route through these contrail forming conditions to minimize both any extra fuel burn to fly lower where the air is denser, it's less efficient, or higher where it takes more fuel to climb, versus the climate impact from those contrail clouds. This is an example of one flight we did. You can see the red dotted line is the resultant flight profile. So we would then give that information back to the airline. They'd replan the flights and then create a viable flight plan. In this case, we just did dry runs. But here's an example of 2 flight plans. So the original flight plan created maybe 160 tons of carbon emissions, but the contrail impact was equivalent to maybe over 170 tons. So total climate impact for that flight was equivalent to 331 tons of carbon dioxide equivalent. the second row there, you see an optimized flight plan, slightly higher carbon emissions. That's because we get some slight inefficiencies if we fly lower or higher, but we had no forcing from the contrails, so 0 tons of carbon dioxide equivalent. So the total carbon dioxide equivalent actually saved 168 tons. So that's quite significant. And where we're trying to get to is then enabling the airline to trade that on a voluntary emission trading scheme. Today, that would be worth over $3,000 at $20 a ton. We're probably about $5 a ton though. So divide that by 4. The point here is that the airline can offset any additional costs and actually make a profit from this by taking this very important action. So this is where we're trying to take some of the best science, find a technical solution, but also back it up with a commercial viable business model. So we did 16 flights in total. We actually modified 10 flight plans, and we proved that we could save up to 1,000 kilotons of 1,000 tons of carbon dioxide equivalent across those 10 flights. So that's on average about 100 tons of carbon dioxide equivalent. We weren't always successful at making a flight plan that was viable, and we had a variability of the additional fuel burn. But the reason for this is we're not integrated into the software that does the flight planning. This was a fully manual process. So with software integration, we're aiming over the next 12 months to work with a large Middle Eastern airline. We're aiming to get to something that looks like this. So we're going to try and minimize the number of flights diverted to about 0.5% of all flights. So for an airline the size of Emirates, that's about 12 to 13 flights a day. It's not very much. And we would solve 20% of the contrails problem. That would be equivalent to preventing 200,000 tons of carbon dioxide equivalent each year. And that would only generate a fuel burn penalty of about 1/100 of a percent. And then if we can convert that into carbon offset credits, that's worth over $3 million to them. So we're really at that point where we're taking something incredibly new to market. And then if we can prove this, all the airlines will be following this model. So yeah, the long-term goal, integrate with all flight planning software providers, and then scale up this carbon offsets trading. And we really want to support that journey towards the full closed loop of offsetting, where we're making sustainable aviation fuel in the future. So yeah, that's my talk. I tell you what I'll do. I'll quickly share the contrails forecast for today. So hopefully you can all see this. But this is a 24-hour simulation. It's for today. You can see Britain there. These are red areas where you're going to get contrails that will have an impact on climate. We've got the animation going through 24 hours, time steps, and this is flight level 370 at the moment. So that's 37,000 feet. If we go up to 41,000 feet, you'll see lots of green disappear. Well, it's just green, there's no more red. If we go down to 330, so that's a fairly common cruise altitude, you're seeing lots of red areas. If we go a bit lower, we're down to no contrail forming conditions. So what the software does is it actually finds the optimal way through in time and space to minimize the climate impact from these contrails. And so our next step is to automate this to get the maximum benefit from it. So yeah, that's the end of my talk. Thanks very much. I'm happy to take any questions.
Thank you so much, Adam. That was really fascinating. And I must say, your presentation has been so good that I've been getting questions throughout it, and you've been answering them as you've gone through. So thank you for that really thorough explanation of your work. I have a few questions about the legislation that's being produced, and you were speaking about some regulations that are going to come into play. And the first is whether or not your team has provided research or advice in any way, consulted in any way on what this legislation will say exactly, and what it will impose on airlines.
Yeah, that's a great question. So we're trying very hard to join working groups and contribute as much as we can. So We're in touch, for example, with the Royal Aeronautical Society and NATS, so they're sort of really leading some of the thought leadership on this issue. And the work that we're doing with commercial airlines, with the support of some of the biggest Middle Eastern airlines, will really help to inform, I think, how the regulation, the future regulation, should be shaped. But it also does all point towards having more flexibility around air traffic management. So at the moment, there's quite rigid rules around what flight levels you can fly at, separation distances, and we are moving towards a more dynamic system. So that would be a great enabler as well. So I think honestly this will take of the order of a decade or more really to fully optimize and scale, and we're at the sort of beginning of that journey at the moment.
Thank you. And will regulations only affect commercial airlines, or do you think they'll also be applied to military aircrafts, for example?
Oh, well, it's interesting that you should mention that. So we're in touch with a consortium of business jet operators, so they're very interested about how they can support the issue and take some action on it. We're also in touch with a part of the Royal Air Force that deals with innovation, and we're hoping to engage with them shortly, actually, on the issue, plus some other issues. So yeah, absolutely. Defense aircraft, there's a lot of military transport aircraft. They're big, heavy things. They burn a lot of fuel. And it's certainly something we could work with. Well, we could work with those defense organizations just as we can work with civil aviation. There's also some interesting other use cases around defense aircraft. Sometimes they don't want to make contrails for other reasons. They don't want to be seen, or perhaps they do want to be seen as a show of force. So actually the contrail forecasting comes from the 1950s, when the Americans were doing U-2 flights to do surveillance over other states, and they realized that their aircraft were making contrails. They needed to find a way to minimize their being detected from the surface at the time, because there wasn't really the other space infrastructure in place to do satellite observation. So yeah, that's really where it's come from.
Thank you. We have another question here in the chat, which I think you may have answered slightly already, but we have altering a flight plan to reduce the production of contrails could involve burning more fuel. How will airlines be compensated for producing fewer contrails to offset this increased fuel cost? Yeah,
absolutely. So this is the biggest challenge of getting this into flight ops. So the first, I guess, a key point is the forcing from the clouds is many times stronger than the forcing from the carbon emissions. So when you convert that into a carbon dioxide equivalent amount for a flight that forms contrails that persist for many hours, it's going to have a vastly greater forcing on climate. So if we can prevent that, the equivalent amount of carbon dioxide we save is many times greater than any additional fuel burn and emissions that we create. So we just target those flights where there's long time spent in contrail forming conditions and the contrails sit there for many hours. We're not going to do all flights, mainly probably only up to 5%. We've proved that we can flight plan without any access to the aircraft performance model, without access to the air traffic management rules, and still only really get on average about 2% to 3% fuel burn penalty. So if you scale that, even at that pretty poor performance, 5% of 2% is, thousandths of a percent or maybe tenths of a percent across all flights. So it's not going to become an issue. And then if we can trade the carbon offset credit we create, that will then offset the cost of the extra fuel. So it's a little bit counterintuitive asking the operators to burn just a little bit of extra fuel, which creates extra emissions, but actually saves quite a bit of the climate impact.
There's another question there. How is the RF of contrails affected by the presence or absence of other cloud layers?
That's a great question from Dougal. So during the daytime, you have sunlight coming in from the top of the atmosphere. If you've got an optically thick contrail layer, so that means the sunlight has trouble penetrating through it, you get more reflection. And that means the sun's energy is going back to space instead of warming up the Earth. So in some cases, you can get a localized cooling effect. If there's cirrus above the contrail, that can have an effect too. Probably again, reflection, or at night time, it might capture some of the infrared energy. The same with cloud layers below. But when we do our modeling and forecasting, we take account of all of this. So we're focused on generating highly accurate vertical profiles of temperature and humidity. We have a cloud microphysics model that enables us to actually to simulate the clouds that are formed, and we take into account, using radiative transfer, all of the effects of pre-existing and contrail clouds to get to a net effect at the surface. So it's quite a mathematically challenging problem, but luckily we've got some fairly smart people in the team, smarter than me.
Are you facing any big opposition with your plans? I mean, what could you tell us maybe who are the big challengers, if there are any?
Well, I guess our closest challenger is DLR in Germany. They've been doing it for longer, but there really aren't that many organizations doing the same stuff. So the reason we were in the right place at the right time with the technology is because we'd spent 3 years building the platform technology to actually do forecasting of small ice crystals at cruise altitude. So it's you know, take Air France in 2009, that was brought down due to icing of pitot tubes that measure the speed of the aircraft. There's been lots of events where aircraft have flown into high altitude icing conditions. So deep convection, really big thunderstorm, mesoscale convective systems transport loads of energy and water up to cruise altitudes. It comes up very quickly, and you make large numbers of very small ice crystals. So those can also clog the compressor of the gas turbine on the engine. So we've worked closely with Rolls-Royce on this issue. And that's really why we developed the capability. So we run our model at resolutions that aren't typically done for weather forecasting, much finer. It uses more compute, it uses more storage, it costs more, but you have to do it to get the weather accurately done at cruise altitudes. So then to do contrail forecasting was a logical step from the cloud microphysics modeling that we were doing. But yeah, it's something we've been working on for several years, and I think because of the issue we were working on, that puts us in a sort of highly competitive position for solving this. Plus, we've made science models that are typically run on institutional infrastructure. So, you know, take NCAR in the States. This is where the WRF model came from. They have a supercomputer. It's in and it's buried in a mountain in Wyoming, and it takes lots of people to maintain it. It costs a lot of money. It's paid for by the government, but the scientific code runs quite well on a known piece of infrastructure. When you start moving that scientific code into the commercial cloud, then you get all kinds of problems. So we've spent a lot of the last year or so just trying to make these models work reliably. And that's basically how we're going to be ahead of the competition, because everybody else trying to do this will have to go through the same learning processes. So we've got a head start, but I'm sure there'll be some competitors coming shortly.
Thank you so much, Adam. I think that was all of our questions. So we'll end it for today. But thank you so much again for taking the time to share this with us, and for that really wonderful and fascinating presentation. And thank you also to all of you who have attended and for submitting your questions. I hope you enjoyed it as much as I did. And we really hope that we'll be able to welcome all of you back at Clare soon. Thank you again, and have a good night.
Bye for now.